In this lesson, we're going to review how to find another point of concurrency. So remember, our points of concurrency that we've talked about so far was we talked about the circumcenter, and that is when three perpendicular bisectors of a triangle intersect. And what does that look like? Again, remember, you bisect the triangle, draw a perpendicular line, and do that to all three sides, and that is the circumcenter. And it's the center of a circle, so it is equidistant to the angles, because this triangle, all the angles are on the edge of this circle. That's the circumcenter, is the center of the circle. So then we talked about the centroid, which is the center of gravity, and now we're going to talk about the incenter. So it's going to be solved the same way whether or not it's on the graph for my class. The incenter is the point of concurrency of the angle bisectors of a triangle. Now remember, to create angle bisectors, what we did is we first measured the angle with a protractor, and then we bisected it. And to bisect means to cut into two equal parts. So how are we going to do that with a protractor? We're going to bisect that, whatever the measure of the angle is. Like, let's say it's 50 degrees. Bisecting it would be 25, and then put a little dot at 25, and then we're going to draw from the angle to that little dot. That's how we're going to easily bisect the angle. There's other ways to do this, but I think this will be easy enough since we're learning a lot right now. So let's do this on three different triangles: the acute, the right, and the obtuse triangle. So for the acute triangle, for the right triangle, let's measure this angle right here. Remember, you put the little dot on the protractor on the angle, line up the side, and then this is an acute angle right here. So when I follow it up, if there are two sets of numbers, I'm going to use the acute numbers, the smaller numbers. So this is about 51, 52 degrees, and when I bisect, that means half of 52 is 26. So finding 26, I'm going to put a little dot there on my paper, and then I'm going to connect the angle I just measured and the bisected value, and I'm going to draw a line. And that should look like you split the triangle, or sorry, the angle in half right there. Not the triangle in half, right? Like, this is different than this. Okay, let's bisect another angle. So this is my 90-degree angle. Sorry, my animations, it should be a little bit over, but my animations aren't perfect. 90-degree angle, when I bisect it, I get 45. Put a little dot at 45. Then I'm going to connect the angle I just bisected, and I draw my line, and then you do the same thing with the third angle. They're all going to intersect at the same point. So in my acute triangle, it's on the inside, and my right triangle is on the inside, and my obtuse triangle is on the inside of the triangle. This is the incenter. Now, how do we apply the incenter? What is the whole point of it? Well, the incenter, if I connected it to the sides at 90 degrees, they're all going to be equal to each other. Let me scoot that up. So if I connected my incenter, sorry, my animation, I scooted that line over on accident. If my incenter is right here, and I draw a 90-degree angle, a segment that's 90 degrees with the side, here, this one's better, then it's going to be the same thing as if I draw a 90-degree segment here, and a segment that's 90 degrees with this side. These three segments are going to be congruent to each other. So we say the incenter is equidistant or equally distant to the sides of the triangle at 90 degrees. Not at the slanted distances. It's got to be the shortest distance, which is perpendicular with the sides. So we can solve some problems. So if I draw my 90-degree segments, these three purple segments would all be equal to each other. And the reason why is, remember, we have our circumcenter equal to the angles, so it's the center of a circle where the triangle's angles are all on the triangle. Well, the incenter, I can draw a similar triangle, but this side, this triangle, sorry, the circle is on the inside of the triangle. So the radius here, the radii here, are all equidistant to my triangle. Okay, So let's imagine that I had a full triangle going on. I didn't draw it all, but let's imagine this was a full triangle. So I bisect my angle. Whoops, my drawing's not very good. I bisect my angle, and if I could draw a little bit better, that means that point S would be my incenter. So since point S is my incenter, these angle bisectors right here, fun fact, if I, again, connect it, oh, I cannot draw right now. If I connect my incenter to my sides at 90 degrees, it's going to be the radius of this circle. So this blue line, 5x, and this other blue line, 6x minus 5, they're going to be congruent to each other. So the incenter will create congruent segments only if they're 90 degrees with the side. So I can say 5x equals 6x minus 5, and then I can solve that problem. I'll subtract 6x from both sides, I get negative x equals negative 5. Multiply by negative x, I get x equals positive 5. Okay, so again, even though I didn't draw the entire triangle, hopefully you recognize, I don't know why it's so sloppy, but hopefully you recognize that if I bisected the angles, point G would be my incenter. So if I draw my inside, if I draw my inside circle, I don't know what's going on with my drawing skills, then these blue lines, these blue segments, are all going to be equal to each other because they're all the radius of the circle. So again, angle bisectors create these congruent segments only if they're at 90 degrees with the sides of those angles. So that means x plus 11 is going to equal 3x plus 1. Use your algebra skills to solve this. If I subtract x from both sides, I get 11 equals 2x plus 1. Subtract 1 from both sides, I get 10 equals 2x. Divide by 2, I get 5 equals x. Now here's an application. Let's say that my husband claims that this park right here, Estes Park, is equally far from these three main highways. Highway 20, Highway 287 is right here, and then Highway 67. 287 kind of merges with 360. So I'm going to roughly apply the incenter. I'm going to draw myself a triangle. So make yourself a triangle using straight sides. And your triangle might be different than my triangle, but it's roughly following these roads, these sides of my triangle. And remember, it's an incenter application because if I want to be equally far from the sides of a triangle, then that is an application of the incenter. And a highway is a straight path. Well, it's a path that might be straight, relatively straight. So we're going to assume that that is the side of my triangle. So we're just kind of estimating here. This is a very loose application. So how do we find the incenter? We bisect every angle and find out where they meet up. So if I were to bisect this angle, I can kind of estimate where it is, but let's use the protractor to measure it, mark the halfway point for the angle, and then draw our little lines. So here is my rough animations of bisecting the angle, and they all meet up here. So was my husband right? Yes. Did he actually say this? No, he didn't. But I could double check this by connecting these to the sides at 90 degrees. And it'll be a lot better when y'all do this on your paper. So again, you draw your triangle, and then you're going to get that protractor and you're going to measure the angle and divide it by 2. So again, this is just a little rough estimate. Measure your angle, bisect it. And it should look like it's bisected. This is a little off again because I'm trying to draw this on the computer. I didn't use a protractor here. So relatively close to Estes Park. It's actually in Joe Pool Lake area. But that's that whole chunk that he was saying. So if he had said Southeast Arlington was equally far from those highways, that's obviously not true, but we still need to prove by finding the incenter. And you can draw yourself a circle. Oops, where's my pen? Draw yourself a circle. I'm going to try using the pen again. I don't know. It's a little spotty. And then realizing, hey, if I look at my radius to the side, my radius to the side, my radius to the side, those three lengths should be congruent if I measured probably in centimeters on your paper. Okay, so that's our notes. Make sure you grab the worksheet and work on that, and we'll tape that in there once I'm done grading.